Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at carbonyl compounds and more specifically the reduction reactions of carbonyl compounds. Right, so this is following on from the video of forming carbonyl compounds through the oxidation of alcohols. Okay, so I'd like you to open up your booklet and we will get started. Okay, so aldehydes and ketones can undergo reduction reactions to produce an alcohol. These are called nucleophilic addition reactions, which is also the name of the mechanism. Okay, so we can take an aldehyde and we can reduce it, and if we reduce an aldehyde we would form a primary alcohol. If we had a ketone and reduced it, we would form a secondary alcohol. So it's just the opposite of oxidation of these two alcohols. So we need to use a reducing agent to use this, and the most common one is NaBH4. And this is known as sodium borohydride. You just need to remember that it's NaBH4. You may see it called some different names, doesn't matter. Okay. And NaBH4 is a source of hydride ions, so my H- ions. And rather than writing this in the overall equation, we can just represent it as H. Very similar to our oxidizing mixture, our oxidizing agent, which we described as O in square brackets. Okay, moving on. So aldehydes, as we said, are reduced to a primary alcohol. So I'm going to give you an aldehyde and I want to see if you can work out what the alcohol will be. I'll give you a couple of minutes. Okay, I'm sure you've been able to figure this out. So if we've got our aldehyde, we're going to produce our primary alcohol, which will be ethanol. Remember, we need to balance the oxygens. Oxygens are already balanced. Balance the hydrogens, so 4 on this side, 6 on this side, so I need a 2 here. Reducing agent, as we have said, is, NaBH4. Conditions, there are lots of different conditions, but really we just need to warm it. You might see reflux as well. Okay, so moving on. So ketones are reduced to a secondary alcohol, and this time I'm going to give you the secondary alcohol, and I want you to come up with the ketone it was made from. Okay, I'm sure you'll figure this out as well. So because we made a secondary alcohol, it must have come from a ketone, and this is propan-2-ol, so prop and 2, so it must have come from propanone. I've balanced my oxygens, I've balanced my hydrogens, so I can move on. So my reducing agent again is NaBH4. Conditions, I'm just going to write warm, and that's it. So LiAlH4 is a much stronger reducing agent. This can also reduce a carboxylic acid. Okay, so I'm going to give you a carboxylic acid, and I want you to think what it will be completely reduced to. So have a think back to the oxidation of your alcohols if you're a bit stuck. Okay, so we know that a primary alcohol will be oxidized completely oxidized to an ethanoic acid, so that stands to reason that an ethanoic acid that is completely reduced would be to ethanol. Okay, so the only tricky thing about this is we've only got one oxygen in our alcohol compared to 2 oxygens in our carboxylic acid. Therefore, we need to balance it with H2O, which means we need 4H. So our reducing agent that we would use would be LiAlH4. It would occur at room temperature. And another condition, you don't really need to know this, but I'll write it in, is that it needs to be carried out in a solution of ether. It gets a bit complicated, so we'll just leave it as that. Okay, moving on. So, the difference between C double bond C and C double bond O. So both C double bond C and C double bond O have a double bond, unsurprisingly, because I keep saying it. This means they can both undergo addition reactions. However, the mechanism for the addition reaction is different. And the reason why is because of the difference in electronegativity between the carbon and oxygen atom. Oxygen, as we know, is more electronegative than carbon. Therefore, the C double bond O is polar. And this means nucleophiles are attracted to the positive carbon. So, if you think back to your alkene mechanism, that was called electrophilic addition, because the electrophiles, which like electron-rich areas, are attracted to the double bond, so the electron-rich area. Nucleophiles like electron-deficient areas, so positive charges. Okay, so that's why we have a different mechanism. Okay, so moving on to our reaction mechanisms. So reaction mechanism, so reduction to an alcohol when we're using a ketone or an aldehyde, and we represent the nucleophile as H-, and this is from our NABH4. That's our source of our nucleophile. Okay, so we will start with ethanol, I think. So I have my ethanol, I have my nucleophile, and I have my polar bond because oxygen is more electronegative than carbon, and therefore my nucleophile, a lone pair of my hydride ion, is attracted to my positive carbon, which breaks the double bond meaning we form this intermediate which is negatively charged. Now we have some water knocking around. Okay, which means that my lone pair of my oxygen is attracted to this hydrogen atom, which breaks my covalent bond in my water. To form my product. Okay, I just want you to have a look at the, we'll go through this first. Okay, so explaining this mechanism. So the lone pair on the hydride ion is attracted to delta positive carbon. This forms a dative covalent bond between the hydride ion and the carbon and the delta positive carbon atom of the C double bond O. The double bond in the C double bond O breaks via heterolytic fission to form a negatively charged intermediate. The lone pair on the negatively charged oxygen atom, forms a dative covalent bond, or just covalent bond. Oh, sorry, I've already got covalent bond, so just dative. So a dative covalent bond with the hydrogen atom in water. The covalent bond breaks to form a hydroxide ion. This is known as protonation by water. Okay, so we'll just explain this. So first bit, the lone pair on the hydride ion is attracted to the delta plus carbon. This forms a dative covalent bond, so this would be my dative covalent bond that forms. The double bond breaks via heterolytic fission, and it forms this negatively charged intermediate. The lone pair on the negatively charged oxygen atom, so here's my oxygen atom. The lone pair forms a dative covalent bond with the H atom in water, so that's here. The covalent bond in the water breaks and forms a hydroxide ion, and obviously my product here. Okay, so just quickly, I'd like to have a go at naming what the starting reagent was and the final product was. Okay, so we've gone from our ethanol to our ethanol. Okay, so the overall equation, so I'm going to use my, I'm going to use H to represent my reducing agent, which means I'm going to have CH3CHO goes to CH3CH2OH plus 2H. Okay, right, so moving on. Reaction of carbonyl compounds with HCN. So why do we do this? We do this to increase the carbon chain length, which is useful in organic synthesis. A mixture of sodium cyanide, so NaCN, and an acid is used to provide HCN, as HCN is an extremely volatile liquid and it turns to a gas at a low boiling point. And HCN is quite a toxic and poisonous gas, so usually we use NaCN and H+ to produce the HCN. And the product formed is called a hydroxynitrile. Okay, so my reaction mechanism is, so I'm taking my aldehyde or my ketone, I'm reacting it with HCN and I'm reducing it to a hydroxynitrile. Okay, I'd like you to have a go at doing this. I'll give you a starting point, see if you can figure it out. So, again, let's use ethanol. And instead of my hydride ion, I'm going to use my cyanide ion. So this is my nucleophile. Okay, have a go at trying to do this mechanism and then we'll go through it together. Okay, I assume you've got something that looks quite similar to this. So we'll talk through it. So our nucleophile, our cyanide ion, is attracted to the delta plus carbon. This breaks the double bond. Then the lone pair on the negatively charged atom is attracted to the H+. This H+, remember, we've acidified our NaCN, so we haven't got any water. We can just add the H+ here to produce this. And if I was going to name this, I would name this as oh, excuse me, what have I done wrong there? I have missed my OH. Helps if I do that. So this would be called 2-hydroxy propane nitrile. Talk about the naming in a little bit. We'll just go through our formation. Okay, I'm just going to pause for a second because my computer seems to be playing. Okay, I'm back. I think I've got it working again. So we were going to go through the description. So it's very similar to the other one we were doing. So the lone pair on the Cn- ion, so this is just instead of my hydride ion, it's attracted to the delta positive carbon atom. This forms a dative covalent bond between the Cn- ion and the carbon atom of the C double bond O. The what are we on? The covalent bond, no, the double bond, excuse me, in the C double bond breaks via heterolytic fission to form a negatively charged intermediate, and the lone pair on the negatively charged oxygen donates a lone pair of electrons to a H+ ion. This is known as protonation. Okay, so I'm not going to go through all this again, it's pretty much exactly the same. The only difference being is that we have the nucleophile as a cyanide ion, and instead of using water to protonate, we are protonated using H+. And as we said, it's called this is called 2-hydroxypropane nitrile. Okay, so I'm going to write my overall equation. Instead of using H square brackets as my reducing agent, I can actually write HCN in here. So now I would take my ethanol plus HCN would form CH3 CH OH CN. Okay. Right, so naming hydroxynitriles. So the CN is always position number 1. And I'm going to draw one. And I would like you to have a go at naming this hydroxynitrile. Okay, I'll give you a... Okay, so we know that the CN is always position number 1. That's what we've said up here. The longest carbon chain is 1, 2, 3, so it must be propane nitrile. We also have a hydroxy group, an alcohol group on the second carbon, so 2-hydroxy. But we also have a methyl group, so it must be 2-hydroxy, 2-methyl propane nitrile. Okay, you've got a couple of questions to do. I'd like you to have a go at them, and I'll give you about 10 minutes. Okay, so let's have a quick go through the answers. So our butanol, so it's our aldehyde, is going to be reduced to a primary alcohol, which would be butanol. Because we're using NaBH4, we would represent our nucleophile as a hydride ion, so it will attach to form a dative covalent bond with our delta positive carbon. The bond will break, like I've forgotten something. The double bond will break. To form our O-, negatively charged O- atom, it will be protonated by water to produce our our butanol. Don't forget your OH-. As you can see here, I have just put, I didn't write all of this out because you don't need to. The bit you're looking at is the end of the chain, the aldehyde group, the carbonyl group. Okay, moving on. So I have my butanone, I'm reacting it with HCN, so I can actually write this in, and I'm going to produce a hydroxy nitrile. And if I name this, it would be 2-hydroxy, because I'm starting from here, remember, so 1, 2, 3, 4. So 2-hydroxy, 2-methyl, butane, 1, 2, 3, 4, nitrile. And my mechanism is going to be very similar to the one we've just done, but I'm going to use a cyanide ion. I'm going to break the C double bond O, and instead of using water, it's already acidified, it's in an acidic solution, so I'm just going to protonate it using H+. plus. Okay, so that's it for today. I hope that was useful, and I will see you next time. Okay, bye bye.